Okay, hi. Myself, I am Prasanna. So I found out something on Collatz conjecture. So I want to share it and establish about that thing. So I'm gonna show you that one. Yeah. So this is what I have documented. It's like 6 pages. So this is the Collatz conjecture. Myself, I am Prasanna Kumar here. So I wanna showcase something to you. This is I found out something in Collatz conjecture. You all know about Collatz conjecture. So Collatz conjecture is something if you is a process of calculations of a particular number before it reaching one. So let's take a number like 8. So if it is an even number, we need to divide it. So it will be 4. And then 4 is also an even number. We need to divide it by 2, and we will get 2, which is an even. And we will divide it by 2. We get a 1. So here 1 is actually an odd number. So what we are gonna do to the odd number is that we will multiply it with 3 and add 1. It will become 4. And as a simplification, I adjust the Collatz conjecture rules in such a way like, so normally if it is an odd, you need to multiply with whatever the number that you got has an odd, and you will add +1, and I will divide the number with 2 for the simplification. And this is the first rule. And then this is another thing that you will get to know, you will understand what I found. So methodology, so you can read whatever I am seeing here. Okay, let's start from beginning. I was searching on Collatz conjecture for almost an year. One day I observed that 2 to the power of n minus 1 sequence numbers are kinda interesting. Yeah, those are 2 to the power of n minus 1, where n belongs to the natural numbers. I want to find out what happens if I do 2 to the power of n minus 1 algebraically. So I was researching on this Collatz conjecture for almost an year. Starting 4 months, I was so confused, I am unable to find anything at all. In the meanwhile, I found out that 2 to the power of n minus 1, whatever the sequence we get, applying n as a natural number, sorry about that, n as a natural number, and then I found a pattern that we can do continuous odd operations to that sequence. So how many times? It will be n times. So whatever the number n we pick, that is a number that odd operation is going to happen. So what I observed in that 2 to the power n minus 1 sequence is doing n number of operations continuously. So I can't say that this will happen for everything, like happen whatever for only happen for some sequence. I need a particular algebraic proof. So here what I have came out. Let's assume x is equal to 2 to the power of n minus 1. So for simplification, I can place 2 to the power of n minus 1 in all the places of x, but so for the simplification I put it as x. So what I'm assuming is that x will continuously do n number of odd operations, so which is network points. Then the first odd operation will be like this: 3 times plus 1 by 2. This is the first odd operation. Second, so if you check it or pause and check it out, we will get that same thing. And third operation, fourth operation. So I found out there is some pattern over there. So except 3 to the power of times x, the coefficient of x, and then remaining all are in a pattern. So I figured it out, and for the nth odd operation we will get this. So these are the middle and n minus 1. You can check it out. And then I want to calculate this value. It is a sequence. So like it is a series. We can find out its finite value. So in that way, so I actually simplified it like this, and then I got what we say, commoned out 3 to the power of n minus 1, because k is the main thing here. So we can't common out the terms that has k involved properly. Here I can subtract 3 to the power of n minus 1 from the sequence. I did that, and to the 2 by 3 summation to the power of 0 to 1, it is very similar summation. If you are any 10th graduate, you will get 10th graduate, you will get to know what you are not supposed to do. And so I did that. So this is the formula. I applied this thing, and I got as a summation value, this whole summation is equal to 3 to the power of n minus 2 to the power of n. So this is the fit. So I replaced it, the entire sequence, with this, and I got n the term, whatever the term that we are gonna have, whatever the number that we are gonna have after doing n number of odd operations to x is 3 to the power of n minus 1, 3 to the power of n and whole minus 1. So this is the conclusion 1. This is a first sequence that I found out long time ago, like 8 months or 6 months ago. So now doing n number of odd operations, and it works for any natural number. Now what I wanted is that 3 to the power of n minus 1 should do continuous even operations. But to do continuous even operations, the 3 to the power of n minus 1 should be a multiple of 2 only. Like so what is the rule for odd operation? It will divide by 2. So if it only need to do continuous even operations, it should only have 2 as its main composite, not one and only composite. But if I check out its sequence and 3 to the power of n minus 1, so it doesn't have that. There are some random numbers, not random, but in a sequence numbers, which are not what I wanted. So I came up with another. Let's alternate the sequence and find out if it's possible to get that. So but it is not. So what if I multiply only 3 to the power of n with some value, say a, and subtract with 1, then I might get some perfect value that I wanted. So from the equation, page number 3, so this is the equation I noted down. I took this that equation and place it here. If x is equal to 2 to the power of n times a minus 1, so what happens? I applied it and I got a to the power of 3 into minus 1. This is the equation. And I am assuming that a times 3 to the power of n minus 1 should be a number that is only multiple of 2. So if number is an only multiple of 2, it will be in the form of 2 to the power of p. P can be any natural number. And a is equal to 2 to the power, I figured it out. I rearranged it. So, and now a should be a natural number, p should be a natural number, n should be a natural number. So every number and every value here should be a natural number, every variable. So to find out that one, actually I applied some logics, like if I want 3 to the power of n should be totally cancel out from the numerator, then the numerator should have 3 to the power of n has its multiple. Okay, so then if I found out the value of a, which should be a natural number, okay with that. This is the table 1 that I found out. So if I apply the value of p only for 2 to the power of plus 1, I got 3. There's a 3 to the power of 1, 3 to the power of 2, and it will continue and have some other multiples, but we don't need that as of now. We need to our primary aim is to cancel out the denominator completely in the numerator. So if the p value is the value that is like a 3 to the power of something, we will get that. We will get three multiples in numerator. So in the equation a equal to the power of plus 1 by 3 to the power of n, numerator 2 to the power of p plus 1 must have 3 multiples, not just 3 multiples to perfectly cancel out the denominator. What I observed in the table 1, page 3, is that all the values of 2 to the power of p plus 1 has 3 multiples if p is equal to the power of n minus 1. So you can check it out whether it is true or not. And so a is equal to 2 to the power of 3 to the power of n minus 1 plus 1 by 3 to the power of n is the perfect value for a. So in this way, a will be a natural number. As per the statement, if a is a natural number, then so I applied a in the final equation. So in this equation, and then I got 2 to the power of 3 to the power of n minus 1. So finally, a to the power a times to the power of a times 2 to the power of n minus 1 will be equal to, after doing n number of odd operations, it will become 2 to the power of 3 to the power of n minus 1, where a is this number. So result. So as I stated that whatever the numbers which are in this form will definitely have these number of steps. So after doing this number of steps, it will definitely reach to 1. This is the proof. So as of now, as we know the final conclusion, does your method work for all the numbers or only some? So no, this equation doesn't work for all the numbers, but I will figure it out future. I will definitely figure it out in future. It's been 11 months that I am working on this one. I might give another 10 months for this problem, but eventually I will figure it out as of now. And then how can you help future researchers on Collatz? So my theory is that this is the first step to solve Collatz conjecture. As of now, as I've known that no one have ever created a formula or predicted such that it for a particular sequence it's not possible to figure out. So there is a normal another sequence. So whenever the number, the x, is in the form of 2 to the power of something, it will be reached to 1 in its power value. So that's the basic knowledge. This is the different one that is related to that. Hope so you guys understand this thing. And yeah, so I will if you want to check this whether it is true or not, I will put this thing in the description. You can check it out.